The goal of our project is to improve the potential efficiency of solar use and to attract attention to the wide variety of capabilities of solar energy. By building the Heliotracker and powering lights, we expose the different uses of alternative energy to everyone who views our project. By making the Heliotracker itself, we improve the efficiency of solar panels by proving how much energy can be harnessed when the solar panel moves with the sun.
We observed that alternative energy, specifically solar, is devoted to being a substitute source of energy in the place of a traditional source, such as small-scale lighting. Solar power only takes up 0.3% of total U.S. consumption of energy per year. However, the installment of solar energy is rapidly growing in the past few years. Solar energy has an incredible amount of potential uses that is being overlooked because of its consumption with conventional uses. The second issue that we solved through this project is inefficiency of stationary solar panels. On average, a stationary solar panel will only absorb 1 hour of direct sunlight every day. However, our Heliotracker will allow for the absorption of 12 hours of direct sunlight every day.
Our project is the solution to these problems because the solar panel that follows the sunlight will capture the energy more efficiently than traditional solar methods. Our Heliotracker will follow sunlight throughout the day, therefore collecting the most amount of UV rays possible.
To begin designing our Heliotracker, we first researched many different design possibilities for the machine. Then we researched the optimal angle at which our machine needed to be structured based on our geographical location. We figured out that at the Houston, Texas latitude of 29.7604 degrees, we must tilt our solar panel 50.7 degrees for optimal solar exposure.
We constructed the basic frame on which our solar panel will lie. Our challenge was to determine how to allow the solar panel to rotate. After trial and error, we slid metal rods through an L-shaped framing pieces attached to the edges of the frame. This allowed the linear actuator to have complete range of motion. We then mounted and wired the solar panel to the battery and set it up in the sun to test its energy capacity and efficiency.
We installed the linear actuator near the base of the stand in order for all of the rotation of the solar panel. We then attached the primary solar sensor to the top of the base. This sensor's purpose is to relay sunlight levels to the controller. Next, we installed the solar tracking controller which connects to the linear actuator. This controller's purpose is to send signals to the actuator of how far to extend or retract throughout the day.
Next, we wired our battery to our solar panel. We placed the wires and battery into a plastic bin to waterproof these supplies, and when the battery was fully charged, we wired one of the garden lights to the battery as a test. This was a very important step in our project because the light would tell any error in electrical calculations. The light turned on, so we wired the remaining lights and positioned them in the trees. When all the lights turned on, our project was successful. With the installment of solar energy rapidly growing in the past few years, people with stationary solar panels are not receiving the full benefits of going green. They are absorbing less sunlight with stationary panels, and with a Heliotracker, more energy can be absorbed, overall increasing the efficiency of the entire system. In the long run, more energy can be absorbed, which allows endless possibilities on what it could power. One Heliotracker can do the job of many stationary solar panels.